Hi, I am MAISARAH, and today my team and I will be discussing about the classification of air pollution data. Air quality had become a significant problem in our everyday life, especially for those who live in the industrial region. Our study is aimed to analyze the effect of air quality index on the health impact score. There are a few problems that are expressed in this study. The first problem statement that was identified is what is the correlation between air quality index and health impact score. Next is how do different health impact classes respond to varying levels of AQI, which is air quality index. The objectives that we aimed for our project is to develop a predictive model using classification techniques. Other than that, this task is also aimed to analyze how various health impact categories react to different levels of air quality index. For the dataset that was chosen, it was sourced from Kaggle and focused on air pollution metrics. The dataset contains detailed information regarding the air quality and its impact on public health. For the dataset, there are 12 recorded variables available. The first one is air quality index or AQI, which measures how polluted the air is. Next, there are PM10, PM2.5, NO2, SO2, and O3. It is the measurement of concentration of particulate matter that has the diameter less than 10 micrometers, 2.5 micrometers, measurement of nitrogen dioxide, sulfur dioxide, and ozone in the air respectively. Lastly, there are also the health impact metrics, which consist of health impact score and health impact class.
Assalamualaikum warahmatullahi wabarakatuh. My name is HAZWANI NURIN ATHILAH BINTI ZAINAL. Let's talk about the methodology of VIEW. This project addresses a public health challenge by predicting health risk levels from air quality measurements. The problem is framed as a multi-class classification task, where the continuous health impact score is grouped into 5 discrete classes. Class 0.0 equal to safe, classes 1.0 to 4.0 equal to at risk, with increasing severity. This supports real-world decision-making, such as issuing targeted health alerts when risk crosses a threshold. A decision tree classifier was selected for 3 key reasons. First, it provides full interpretability through transparent, rule-based logic. For example, if air quality index larger than 150 and particulate matter 2.5 larger than 60, then risk level equal to 3.0. In healthcare, this explainability builds trust with non-technical stakeholders. Second, exploratory analysis revealed nonlinear step patterns between air quality and health outcomes. As shown in the scatter plot, health risk does not increase gradually. It jumps sharply once air quality index exceeds 200 to 300. Decision trees naturally capture these thresholds through recursive splitting, unlike linear models. Third, the model is robust to outliers, which are common during haze events. Since decision trees split data based on rank order rather than absolute distance, extreme pollution spikes do not distort predictions. While ensemble methods like random forest may offer slightly higher accuracy, they act as black boxes for this application where transparency and clinical accountability are critical. The base decision tree provides the right balance of simplicity, performance, and interpretability. Let's prediction. Now let's talk about data pre-processing. The dataset contains 5,811 claim records with no missing values. Before training, essential pre-processing steps were applied. The original continuous variable health impact score was converted into a categorical target variable named health impact class, with 5 risk levels ranging from safe to very high risk. The identifier column record ID was removed as it carries no predictive value. The remaining 12 features were retained, including air quality index, AQI, particulate matter 2.5, particulate matter 10, nitrogen dioxide, ozone, temperature, humidity, wind speed, and health indicators such as hospital admissions and respiratory cases. No scaling or normalization was applied, as decision trees do not rely on distance-based calculations. This preserved the original units, such as micrograms per cubic meter for particulate matter 2.5, making results easier to interpret for domain experts. Finally, class imbalance was acknowledged. Over 82% of records belong to class 0.0, which is safe. Although no resampling technique was used, evaluation prioritized F1 score over simple accuracy to ensure reliable detection of rare, high-risk events.
Assalamualaikum, I'm Illiyyin, and in this video, I will be presenting about exploratory data analysis, model selection and justification, and also model training and evaluation. Before training, exploratory data analysis is done to better understand the feature relationships and ensure the model choice is correct. Correlation analysis is done using correlations widget in orange to sort features by their mathematical relationship with health impacts. From this, we know that air quality index displays a dominant positive correlation, which is plus 0.615, followed by PM2.5 and PM10, which justifies and proves our focus on these specific pollutants as the primary elements for this classification model. Next, we use scatterplot widget to visualize threshold, which is done by mapping AQI against health impact class. This results in inverted triangle distribution that evidently show that health risks do not increase linearly and hit the thresholds instead. This analysis is important in choosing a model that can recognize the specific thresholds. We choose decision tree as our model for 3 specific reasons. First, for its interpretability. Decision tree creates a clear logic map that is transparent with its reasoning and understandable by us humans. This is called glass box effect. This transparency is vital for clinical accountability, as why a prediction is made is as important as the prediction itself. Secondly, for its non-linearity handling, as our data is not linear. Decision tree instinctively handles step data through recursive split formation, making sure the model's accuracy is not jeopardized. Lastly, for its robustness to outliers, because decision tree is less sensitive to outliers as it divides data into regions instead of calculating an average that would be skewed by extreme spikes that are often time present in environmental data such as a one-day pollution surge. For training, we use 70 to 30% sampling strategy, in which we use 70% of our 5,811 samples for training the model and the rest for testing the model to simulate how the model would perform in a real-world setting. We can evaluate this model based on its performance metrics, using classification accuracy and F1 score more specifically. F1 score is prioritized here as there is a class imbalance in the dataset, which is they are more healthy than crisis days. The F1 score validates that our model is as good at catching the rare high-risk health events as it is at recognizing normal days. Classification accuracy, on the other hand, shows how often the model gets the correct target. Lastly, we use confusion metric widget to see where our model makes most errors, which are between neighboring classes. In medical context, this is considered as a low-risk error that further confirms the model readiness for pilot testing in our unit. That's all from me.
With our class distribution, we found a massive imbalance. Over 82% of our data is class 0, meaning low risk days are the norm. We have to be careful not to let the model ignore the critical 70% representing higher health risk. Moving to our key risk drivers, we found a clear danger zone. Once the AQI crosses 130, the probability of severe health outcomes spikes significantly. If we can keep the AQI under 100, the data shows we stay mostly in the clear. Finally, looking at the health correlation, AQI is our North Star metric with a 0.615 correlation. It outperforms individual pollutants like PM2.5, proving that health risks are caused by the total toxic soup of pollutants in the air rather than just one single chemical. Moving to model performance, our three-color classifier was highly effective, reaching an overall accuracy of 88.4%. As shown in our classification report, we are extremely precise at identifying safe air quality days with an F1 score of 0.95. However, the real challenge was at the risk categories. Because these events are rare in our data, the performance there was lower at 0.44. Our confusion matrix shows that while we caught 187 at-risk events, we missed about 101. Overall, with an AUC of 76.4%, the model proves to be a reliable baseline for environmental monitoring. The future iterations could focus on boosting our sensitivity to those high-risk categories to further protect public.
Feature importance analysis. Using the decision tree algorithm combined with generation normalization, we have run the top predictors deriving the model precision. First and foremost is the air quality index, or AQI, which dominates the model with a weight of 77.2%. This confirms that overall air quality is the most decisive factor in determining whether conditions are safe or at risk. Next, we have particulate matter. PM2.5, defined particles, contribute 8.8%, making it the second most critical variable. PM10, the coarser particles, adds another 5.9%, reinforcing the clinical relevance of airborne pollutants in respiratory risk. Gaseous pollutant like ozone, O3, and nitrogen dioxide, NO2, play supporting roles with weight of 5.1 and 3% respectively. This helps refine the model's ability to distinguish between moderate and severe risk levels. As shown in diagram 4.3.1, this hierarchy gives us a clear roadmap. AQI is our primary index, followed by particulate and gaseous indicators. Together, they form the backbone of our early warning system for environmental health hazard. Interpretation and significance. Let's look at how well our model performs and why it matters. With an overall accuracy of 88.4%, the system shows strong reliability, far exceeding a random baseline. This confirms that environmental pollutants, especially AQI and PM2.5, are decisive predictors of health outcomes. In public health, recall is our most critical metric. The model correctly identifies 197 out of 298 at-risk cases, meaning it catches the majority of hazardous air quality events. This is vital for early intervention. For the technical summary, validating the safe versus at-risk prototype. From a technical standpoint, the model strikes a strong balance. With a recall of 66.1%, it minimizes undetected risk. Its precision of 83.8% ensures that alerts are accurate, reducing the chance of alarm fatigue. Finally, the F1 score of 73.9% confirms that the system is both sensitive and specific, delivering clinically valid alerts while maintaining reliability across safe and at-risk classification. Conclusion. The study confirms that environmental health threat can be forecasted with high statistical confidence through a decision tree framework by identifying AQI and PM2.5 as the dominant predictors of respiratory and cardiovascular risk. The model demonstrates clear evidence of pollutant-driven health outcomes. With an overall accuracy of 88.4%, the prototype established a reliable, data-driven architecture for an early warning system, bringing the gap between environmental monitoring and proactive healthcare intervention. This validation underscores the model's potential to serve as a practical tool for public health agencies and medical providers in anticipating and mitigating risk. Looking ahead, several enhancements can strengthen the system, predictive power, and clinical utility. Algorithmic optimization through hyperparameter tuning, particulate tree depth and pruning, can sharpen sensitivity to at-risk events. Dataset expansion with medical variables, such as ER admission rates or records of pre-existing respiratory conditions, would refine correlation between air quality and health outcomes. Finally, comparative modeling using ensemble methods like random forest or gradient boosting could benchmark performance gains against the current decision tree baseline, ensuring the system evolves into more robust and adaptable early warning.